Hi everyone, I'm Tawaki, and I'm a PhD student at the University of Toronto, and also a research scientist at NVIDIA. Today I will present our paper, a dataset and explorer for 3D sign distance functions. Datasets have a key part of the history of computer graphics. They provide a reference point to compare existing solutions and identify problems and weaknesses during the development of new algorithms. Some classic examples of this include the Stanford Bunny, the Cornell box, and the Crytek Castle. Recently, we see a trend where computer graphics and machine learning are increasingly intersecting. Datasets, like ShapeNet and Thingy Tenkei, have proved to be valuable datasets which have made immense impact in graphics and machine learning. Another trend that we have been seeing in this last few years is the increasing interest in volumetric representations in machine learning and computer graphics. This includes representations like radiance fields and NeRF, but also things like sign distance functions. Sign distance functions are enjoying a renewed focus of research activity in computer graphics and machine learning. These volumetric representations are being coined as neural fields. We recently also published a Eurographic State of the Art report on these volumetric representations, so be sure to check that out for more details. As such, in our work, we collected reference dataset of 63 sign distance functions of varying complexities for research purposes. These sign distance functions are associated with mathematical formulas which define them. These mathematical formulas have a number of interesting traits which are important to consider when working with sign distance functions. Before we get into the details of all that, let's first understand what sign distance functions are. So what are sign distance functions? Sign distance functions encode the distance to the nearest zero level set, which is where the function equals 0. In 2 dimensions, for example, the height of this function encodes the distance to the contour where the height is 0. In 3 dimensions, the sign distance function similarly encodes the distance to the nearest surface. How can we visualize and render these sign distance functions? We can do this with an algorithm known as sphere tracing, which is a form of ray tracing. Sphere tracing involves marching along a ray to find the nearest intersection of a shape with that ray. Because the sign distance function gives a distance to the shape in any direction, and not just the ray direction, we can use this as the upper bound for how much we should travel along the ray to find the intersection. Once the distance is small enough, we terminate the algorithm. The surface normal can be found by calculating the gradient of the sign distance function at the intersection point. We call this sphere tracing because the upper bound of the step size forms a sphere. There's also a concept of sidedness in sign distance functions. If the sign distance function is negative, as shown here in blue, the location is inside the object. Otherwise, in green, this location is outside the object. This makes sign distance function useful to represent volumetric and closed objects. It can also make sure that the sphere tracing algorithm converges even if it oversteps due to numerical errors or something. Common geometry representations like meshes encode the surface of a shape with a graph structure. In comparison, sign distance functions can be mathematical formulas which define the sign distance to a surface. It is possible to extract the sign distance function from a mesh using an algorithm like the generalized winding number. However, meshes found in the wild can have a number of issues. For example, the mesh can have self-intersections that make the inside-outside classification ambiguous. For example, should the area within the intersected section be inside or outside? They can also be non-watertight, meaning they can have open borders, which also makes the inside-outside classification ambiguous. This is what motivates our dataset, which consists of all sign distance functions defined by mathematical formulas. This, by definition, means that they do not inherit many of the issues that meshes in the wild may have. So our dataset is composed of complicated shapes which are defined by mathematical formulas. Of course, it's not very easy to come up with mathematical formulas for really complicated shapes. So where does the dataset come from? Sine distance functions enable something called constructed solid geometry, where you can combine a bunch of simple shapes for which their formulas are known to create complex shapes. Let's see, for example, how we can make this knob. The base of the knob is actually a combination of two cones, one right side up, another upside down. We then cut out a cylinder from the base and cut a slice of the pie with a triangular prism. We then add a sphere on top and then cut out a sphere again from the sphere. We can then add another sphere inside that hole that we just cut out and add an engraving with a torus. Lastly, we add some beveling and we are done. That wasn't so bad. Using tools like constructed solid geometry, artists can create amazingly complex shapes out of simple primitives, and many of them are available in open source on websites like ShaderToy. This is where we collect most of our data points for our dataset. Sine distance functions collected in the wild can have a number of issues. We call these sine distance functions, but oftentimes, sine distance functions in the wild don't actually represent the nearest distance to the surface. One mathematical property which is necessary but not sufficient for the sine distance function to be an actual sine distance function is the iconal property. The iconal property says that the gradient of the function has to be 1 almost everywhere. More often than not, these sine distance functions do not satisfy the iconal equation. This is because satisfying the iconal equation while creating complex shapes can actually be quite difficult. So why can they get away with this? To understand this, let's consider sphere tracing again. If you remember, sphere tracing uses a distance calculated by the sine distance function as the upper bound of how much you should travel along the ray to not pass the surface. This means if the sine distance function doesn't actually tell you the distance, but gives you a conservative estimate of the distance, you can still converge at the right surface. The algorithm will just be less efficient because it needs to take smaller steps. This is basically what happens for most of these sine distance functions, which are not actual sine distance functions. They just give a conservative estimate. Let's take a look at an example. We noticed that while benchmarking our sine distance functions, that this snake takes a really long time to render. This is because, as you can see from this cutting plane, which shows a 2D cross-section of the sine distance function and their contours, isocontours, that the sine distance function is truncated. As you can see, if you go out farther and farther from the snake, it's a constant color at some point. This means that the sine distance function, after a certain distance, is a constant value. This is a common type of sine distance function you may encounter in the wild. Here's another example. This sine distance function has different kinds of issues, like the sine distance function being discontinuous at certain locations. While this may not be a huge problem in rendering, this may be problematic for other purposes, like for example, you are training a neural network to fit the sine distance function. A big part of our contribution in our work, beyond just acquiring, cleaning up, and normalizing these sine distance functions found in the wild, is that we provide the toolkits to enable you to do this sort of analysis on your own. In fact, we provide an entire visualizer, complete with user interfaces, which lets you analyze these sine distance functions in real time. You can even edit these sine distance functions and reload them on demand. Let's go ahead and take a look at a demo of our Explorer. When you open up the application, you'll see an icosahedron sine distance function. You can toggle appearance settings like the background color and the ground plane color. You can even turn off and on the ground plane. You can also load up different sine distance functions. For example, let's look at the snake. Or maybe a car. To change the appearance of your objects, you can, for example, look at the normals or the mean curvature. You can also use different matcaps for different visuals. You might have like a green automotive looking thing. Or maybe you want something metallic. Let's also look at how this looks like for our knob. We can also make it look like gem. Or maybe you want to do some kind of, toon shading. You can also load up textures using triplanar mapping. And we can also load things like displacement maps and normal maps. Let's also take a look at the cutting plane. We can rotate this cutting plane around, move it around, and also see behind the object by making it transparent. There's also other built-in features in G3D, like a profiler, debug outputs, and also camera settings. We can also edit design distance functions in real time. I'm going to open up Vim right now and open up the shader that defines this knob. And reload the shader. And boom, you see that the sphere inside the sphere has disappeared. And you can also bring it back in. Lastly, let's take a look at some additional capabilities we have. In both computer graphics and machine learning applications, it's useful to be able to export a cloud of points with their associated positions, signed distance functions, and gradients. We provide exactly that. We have implemented a number of different sampling schemes you can use to generate signed distance function values. You can execute these sampling commands purely from the command line. We also provide a direct download for .mpz files, which already have millions of point clouds sampled for you, so that you can load them up using NumPy very easily, and use them for whatever application you want to use it for. See the link down below for more information. In conclusion, we showed that in our presentation the benefits of having an explicit volumetric representation which encodes the signed distance function in comparison to just having mesh datasets. Mesh datasets are great, but they can often be a pain to work with. Our contributions are twofold. First, we provide a dataset of 63 high-quality reference signed distance functions. Second, we provided a toolkit to help you analyze and work with these signed distance functions. Our source code is available in open source on GitHub under the permissive MIT license specifically for the toolkit. There are lots of signed distance functions out there in the world that we have not yet ported into our dataset. We would love to port them all, but also add more features to our Explorer to make it even more useful. Open source contributions to our dataset or our toolkit would be greatly appreciated. Thank you for watching our presentation.